All right, so this is chapter 19, star formation or the birth of stars, from these gigantic clouds to the fragments to becoming protostars and then eventually dropping down onto the main sequence. There's 7 stages, so let's get into it. First of all, the last chapter, chapter 18, really dealt, the interstellar media, the stuff between the stars, shows us there's these huge regions, huge volumes where there's many times the mass of the sun of material, but it's spread out over an incredible amount of volume, many parsecs across. And these things are what we would call the star-forming regions. Mostly gases, but there is some dust and things like that. It's all stuff from the, that we talked about in the last chapter, chapter 18. All right, so just assume that that's there in different locations in the galaxy. How does that stuff eventually form stars? Okay, and so we'll go through all this stuff. We'll talk a little bit about things like brown dwarfs. These are essentially failed stars. Star clusters, how we can test our ideas of star formation using star clusters. These are regions in the galaxy where a whole bunch of stars basically were born at the same time. And this one, Eta Carinae, is a star that's any time could actually die. It's this huge star, huge yellow reddish star or orange, I should say, orange reddish star that could blow up at any moment. Anyhow, we'll talk more about that later. This is what we were talking about, what we mean by these star forming regions where there's a lot of gas and dust, and you can see these are actually the blue dots here are new stars forming. But how did they get that way? That's really what the story of this chapter is about. All right, so star formations happen when part of the dust cloud begins to contract under its own gravitational force. Right, so it begins to collapse. It doesn't completely collapse, but one thing that we know is when the particles, whether they're molecules or just gas or just atoms of mostly hydrogen gas, as they start to collapse, as gravity begins to take over, and even just little subtle hints of gravity take over over large scales, these things will begin to heat up, and there are processes that prevent that collapse from happening. We're going to talk about that a little bit. All right, so here's a region. So let's say we start off with just a few atoms, and just given the spacing of atoms in space, in between the stars, there's really not enough. Gravity turns out to be the weakest of all the forces, and there's actually electrical forces, magnetic forces that if these atoms are charged, that those forces, magnetic and electrical forces, are overwhelming. They'll overwhelm gravity. All right. So anyhow, gravity is just with the density of atoms that you find out there in the galaxy, there's just not enough gravitational force for these things to collapse. And the big reason for this, let's say they're neutral atoms, right? So there's no electrical charge, there's no magnetic field to speak of. Then what happens is, let's say just random motion brings these objects closer together. What that's going to do is that'll cause, motion is heat. Right, so that's what thermal heat, thermal motion is all about, heat, and so heat will easily overcome these really weak gravitational forces between individual atoms, right? And so that, you know, if this was all that was going on, you know, these things would not collapse, all right? And also rotation. Okay, so here's something that happens if of this. So now we're looking at, you know, literally trillions and trillions of atoms. If the overall cloud is rotating, that will actually prevent collapse from happening as well. And also, if there's a magnetic field present, the magnetic field, just like I mentioned a little bit ago, you know, if there's magnetism has to do with moving charged particles that are moving. That's where magnetism comes from. Anyhow, if there's magnetism present, it'll also prevent this gravitational collapse. But of course, we know that gravitational collapses do occur. Obviously, there's lots of stars in the galaxy, in the universe, as a matter of fact. This is an interesting idea, is that the magnetic fields will actually distort the cloud. So they don't necessarily collapse in a spherical manner, at least not at first. So you can just kind of keep that in mind. So these are things that work against it, right? Heat, rotation, and magnetism. All right. So what is it that gets the star, you know, to begin to collapse? It really is. You know, we use computer models for a lot of this. It's, you know, just in a simulation of these huge numbers of particles, of atoms, like I said, mostly hydrogen. You know, if some random motion, you know, assign, you know, various random motions to these things, what are the chances that these things will get close enough for gravity to be overcome, to begin to collapse this object, and especially when you think of, you know, in our computer programs we put in rotational motion and gravitation, you know, rotational motion and thermal motion and magnetism, of course, to see what's going to happen. All right, and oh, by the way, so this table right here, these are the 7 stages of star formation. So we're kind of going to go into this in a little bit of detail. Right now, we're just talking about what's called an interstellar cloud. Right, this is the stuff that we were talking about. Now, so how do you go from interstellar cloud to what's called a cloud fragment? And notice what's going on. So the temperature is going up by a factor of 10. And they're also showing us the time. So the first stage is roughly, you know, from going from interstellar cloud to cloud fragment takes about 2 million years. Right, that's what this number is right here. Notice the surface temperature of this cloud is very, very cold. We're talking about, you know, 10 Kelvin. So, you know, just barely above barely, you know, 10 Kelvin above absolute zero. The central density is in the order of a billion particles per square meter, and the diameter of this thing is huge. You know, this is parsecs across. All right. So anyhow, and we'll go through all of this. So if you notice. When this thing truly becomes a star, you're at, you know, more than 10 million Kelvin. All right, so let's see how this all happens. So the interstellar cloud begins to contract, and this is what we think. Again, we program this. There is actually evidence of this kind of stuff that we have. It's not in the visible part of the spectrum because these clouds block visible light most of the time, and so you can't really see into the clouds, not with the visible part of the spectrum. So usually we use, for example, infrared. At any rate, this right now we're just looking at it as like a computer simulation, but this is what we think happens. Is there, let's say that some cloud some star really far away from this cloud blows up. There's a supernova explosion or something like that. Then that happens with massive stars. We'll talk more about that when we talk about the death of stars. But right now we're looking at the birth of stars. So when there is this pressure that is sent off into space in all directions, when that encounters a star, what happens is that pressure, just like you pushing your hand against the wall. I mean, it doesn't seem like you're doing much, when you push your hand against the wall, but it is like whatever that wall is made of is the particles are compressed a little bit more than they would be without your hand there. All right, so what happens is, over time, as the star begins to collapse, it fragments. So the parts of the cloud, and this is actually a really important step, is that the cloud will break into fragments, and even the fragments will break into smaller fragments. Right, and this can happen so that there are these individual fragments. There are perhaps hundreds or even thousands of these, and of course these are what becomes the stars. Right, sometimes one star, but very often they'll become multi-star systems. Right, like binary systems or even trinary systems, similar to Alpha Centauri. All right, so that's really stage one. Okay, so that there's something that triggers this cloud to collapse, because of course, remember, we just looked at just the cloud by itself can last for billions and billions and billions and billions of years, because there's no trigger to cause collapse to take place. Right, there's more than enough thermal energy to keep the particles away from each other. But if you have this external action where there's some kind of explosion which causes a pressure wave, then the star will collapse or begin to fragment, and the fragments get smaller and smaller and smaller, and that's stage one. Okay, so stage two is when the individual cloud fragments begin to collapse. Okay, so that's these things over here. They'll begin to collapse, and once the density is high enough, then you don't get any more fragmentation. Right, so they're not breaking into smaller and smaller pieces. Stage three. Remember, this is a 7-stage process. The interior of the fragments begin to heat up, so they're going from. Remember, they're starting at like 10 Kelvin, rising to like 100 Kelvin, and then 200, and so forth, because they're as they fragment it, as they get smaller and smaller volume means higher temperatures. The particles are closer together, and really that's a measurement of temperature. So they start to get around 10,000 Kelvin, certainly nowhere near the point where they're going to become a true star. Right? Remember, for something to be a star, the key thing there is hydrogen has to turn into helium. Fusion must take place. All right, so we're getting there. All right, so we're only in step 3. So in step 4, this is the first time that we see on the HR diagram are what we actually call these protostars. So these things are going to meander down, as you'll see that they have these different paths. And eventually drop down onto the main sequence. So that's going to be the rest of our stages. How do we get this protostar to become a star, to ignite nuclear fusion, hydrogen turning into helium, and then these things will settle down and drop onto the main sequence. Actually, how much time do I have? Let me point this out as well. Once the star drops onto the main sequence, it doesn't move from the main sequence. It stays where it is. So wherever it's going to drop on, if it's a really massive star, or it's like an M class star, it stays there. So that once it's on the main sequence, it's just going to turn hydrogen into helium for as long as it has a fuel supply.